We have Jack. Jack is a software developer at LansDB, and he will be walking us through the topic, Supercharging Multimodal Feature Engineering with Lance and Ray. Over to you.
Yeah, thanks, everyone. OK, the mic is working. Yeah, so hi, everyone. My name is Jack. As introduced, I'm a software engineer in LansDB, so the same company as the keynote speaker, Chan, who is our CEO. So this is going to be, I guess, another angle to talk about Lans and also its integration and also its application from the feature engineering perspective. And we can see how things goes. So a little bit about me. I'm a Apache Iceberg PNC member and also Polaris BPMC member. I kind of helped the Polaris to go into the Apache project. Also a Lance core maintainer, of course, as a part of LansDB. Also contributor to a few other projects like Spark, Trino, Ray, those kind of things. Before joining LansDB, I was 7 years in Amazon. So I started with Amazon's internal data lake, just doing table optimizations, making the Parquet tables run faster. Then I moved to EMR and Athena, did quite a few launches with different table formats just to do the integration across the ecosystem. More recently, I was the main designer for the data plan for the SageMaker Lakehouse and also S3 tables. And also, I'm local in Redmond. For anyone who knows Redmond, I live in Education Hill. So, and also, I'm a professional babysitter for almost 2 years now. Yeah. So, I guess as the title suggests, we should first talk about what is feature engineering. And I kind of did this search last night when I was making the slides with ChatGPT 5. So he says that feature engineering is the process of transforming raw data into meaningful features or inputs that makes machine learning models work effectively. It is one of the most important and often most creative steps in building a machine learning system. So I think there is no confusion about that. And for people here who has experience with feature engineering, OK, quite a few. So I guess I don't need to do too much of the introduction. But I think before we talk more, there's a question about, do we still care about feature engineering at this point? And there are some pretty famous people in the industry saying that actually, LLMs don't rely on manual feature engineering anymore, and they learn features by embeddings, as embeddings end-to-end. So from my perspective, actually, we still care quite a lot about feature engineering, and I would say even more than before, because we need good features to learn good embeddings. It's a problem about garbage in, garbage out, and code in, code out, right? You have the raw data on one side, and you have to do all the transformations like data preparation, objective selection, do the tokenization, all those kind of things, adding domain-specific knowledge into the table, and then you go through all the transformations and machine learning process, which produces you meaningful embeddings. And I think it is more important than ever because it is becoming, I think, a trend now that you want to even add embeddings into the set of features you have. And also with LLMs, you can actually generate features, generate content, such as you have a video, and then you can generate captions of the video, and you can add that as a part of your features. And then they can recursively produce even better embeddings and then feed into the system. So comparing to what Chan was talking about in the morning, for the real-time serving use cases, this is even in the feature engineering space itself, it is kind of enriching itself with embeddings and also this kind of generated contents as a part of this LLM generative AI movement. So it is kind of ever more important to talk about how we do feature engineering more efficiently and more productively. And I really like one part that ChatGPT gave me the answer is that the most important part of feature engineering is actually the creative part, that how you creatively make the feature engineering, make more features and make meaningful features that can improve the overall efficiency of the whole system. And however, when we look into this whole process of doing feature engineering, the imagination, the expectation is usually not the same as the reality because we expect that the machine learning engineers, the scientists, the AI engineers can spend most of the time doing explorative feature engineering to create more meaningful features. But in reality, most of your time is taken by preparing the data, building the infrastructure, and doing the integrations. And I think the problem is really twofold, which ties back to the title of the topic about Lance and Ray, which is the problem of the storage and the compute. So the first part is the storage. How do we really store the new features more efficiently, right? So if we look into for example, Hugging Face, what is the most used format today? It kind of extended from the old analytic work. It is a Parquet files. It consists of most of the tabular data today. But if we want to add like a new feature in a Parquet file, it has all these kind of sophistications built into that about how you can do the read more efficiently and do like large scans for OLAP use cases. But when you talk about using that for machine learning and you want to add more features to that, the truth is you have to rewrite the whole the whole file, right? It's like we have built all these sophistications to make the things more efficient, but in the end, you're still stuck with, actually for the machine learning for feature engineering use cases, it is pretty efficient because you have to rewrite the whole thing every time, time. Although we have seen that Parquet files can scale into like terabytes and a very large scale, but in the end, you have like different teams doing different features and different teams doing different data ingestions. All these teams working together, and then they get stuck when things get complicated, right, in a single file system. And then there's Iceberg, right? We are saying that, okay, maybe Parquet files doesn't scale, so we can do many Parquet files and then bind that with more sophisticated metadata layer so that you can do transactions, and different teams can more seamlessly coordinate with each other. This is great, and that is kind of why Iceberg becomes like a standard, the most widely accepted standard right now. However, you didn't really solve the machine learning part, right? Because in the end, the data layer, you have all these metadata pointing to the data files, and those data files still store all the features in a single file. And when we say, for example, if you are familiar with these table formats, we always say that we do schema evolution so that you can update your schema all the time. But that is for the new data. So for example, I have 3 columns and I added 1 new column. That means all the new data are right. All the new data files I add at the data layer will have the 4 columns, but all the old files still have the 3 columns. And when you do feature engineering and you want to add a column, 99.99% of time, you want to do the feature for all the columns, right? Also for all the rows. That means you still have to rewrite the whole file, and actually all the files that you see here. So you are still stuck with this problem, and you're really not solving anything here. So and then people were saying like, oh, okay, now actually I can do multiple tables. And I can store different features in different tables so that different teams are decoupled with each other, those kind of things. That is actually my experience when I was first starting in Amazon. That is, my team maintains the so-called source tables, which are like super important tables, like the clickstream tables, the orders tables. And then there are so many layers of tables dependencies built on top of that, to in the end arrive at the most valuable features that are feed into the machine learning pipelines and to train the AI models. And then you can imagine that all these features, they serve as independent models, and then all these tables have interdependencies that you have to joins, like this row actually match to that row in this feature table, and blah, blah, blah. And that actually makes things even worse to some extent, right? Because you have more dependencies at every single layer, and it just makes things pretty complicated. And remember the title, what I say is multimodal feature engineering, because as the explosion of LLMs, we are trying to use not just tabular data, but actually more and more images, videos, PDF documents, all those kind of things can now become a part of the training materials much more easily. And when that comes, even like the Parquet and Iceberg world is not that efficient, because those are designed for tabular data, which is usually like 145 bytes per row if you look into the standard benchmarks. And then embeddings is much larger, like 25 times larger. And then you have images and videos that are exporting things up. So that is really making this whole feature engineering process even more complicated. And when we look into customers, like all the frontier models, model companies, or the research institutes, this is really making there's a whole infrastructure team that has to be built into supporting all the scientists into building all these kind of things. And some people, I think there was a talk yesterday talking about web datasets and saying that can really solve the problem. Like scale into very big scale. I think that is probably not true for the feature engineering case, because in the like web data set, also a pretty common use case in like Hugging Face, you can see. That is essentially you have a list of tar files, and then you have, in every single tar file, you have samples, and the samples are like JPEG files and JSON metadata and all the other things. And the same problem still exists, right? If you add some new metadata in the JSON file, and you want to apply that to everything, then you essentially rewrite the whole thing. So, so that kind of the problem still exists. And well, what we really are thinking about is there like a perfect solution to all these problems? And what I hope if I told you if that really exists, and that is actually not really Lens in the past, because there was a chance that Parquet could have solved the issue when we look into the metadata, because the Parquet has this layer of files and then column groups and then column chunks. And then inside the column chunk, if you look into the metadata, there's actually an interesting thing, which is a file path. So that means actually in the old days, the Parquet people were thinking about actually can I store the column chunks in other files, and then you can have different files stored in different columns, and then you can actually add columns pretty easily. Although you have to rewrite the footer because the footer still records all the schema. So there was a I guess alternative universe that Parquet could have become much more friendly with machine learning workloads. However, there are a few things that kind of prevented Parquet from doing that. I think the first thing is that the Parquet version evolution has been pretty slow. It has, like the cautiousness of Parquet, which makes it successful, also makes it pretty slow to evolve over the course of time. And it was originally designed for HDFS, which makes this feature pretty useless. And even today, when we see all the Parquet readers and writers, this feature is basically not implemented. And although it's not marked as deprecated, it's essentially deprecated. So the true thing, I think, for Lens is really, let's build the true Parquet, like what Parquet really meant to be. Like when we say Parquet, like the original meaning is really the geometric mosaic, right, for the flooring, like this kind of thing. And can we have that for our data so that we can not only grow data vertically, adding more rows, we can also grow data horizontally by adding more columns. And that is really what, in the end, Lens was trying to become. That is the true Parquet that is much more friendly for machine learning workloads. Like, for example, here, this is the table format kind of conceptual idea. Like I say conceptual because all the fragments are inside the manifest. But like when we look into the fragment, for example, I have a table here with 3 columns, like column 1, column 2, column 3. The fragments actually can store different columns in different data files. These data files also in Lens file format. But you can see that the first column is stored in the first data file, and the column 2 and column 3 are stored in the second data file. So that if you want to add a new column when you are doing feature engineering, that is as easy as you just write new files and then you add it into the table, right? And that is what we call data evolution, which is more than just the old school schema evolution that is like popularized by I would say the first generation of table formats like Iceberg, Delta Lake, Hoodie, those kind of things. So that you, as the graph shows here, you can define for example, UDF, and you can say that the data set add columns to that UDF that will generate you a new file. I guess multiple new files, and those can be vertically appended into the table, which can be used as a part of the feature engineering process. And then you can actually become this both horizontally growing and also vertically growing mosaic of Parquet. So here's an example, like some customers we actually serve. This is a simplified version for example, users like Midjourney. They have you have a bunch of images sitting in the initial Lens table, and then you can run different models, right? DeepSeek and Gemma, and all these kind of things. You can generate captions, you can generate embeddings, and you can run taggers of your captions. You can do all those kind of things kind of recursively. And the rectangles you see are really just new columns in your Lens table and the diamond shapes are kind of the transformations that can be run on CPU for lightweight things or can be run on GPU for more heavyweighted things. And now the concept of having column chunks in Parquet become just individual data files. Now the row group thing kind of become obsolete almost, because that is really represented by the fragment here in the lens table format, right? If you think about that, given that we are storing this in object storage, and object storage have, like from user perspective, infinite amount of storage space, and give you much higher throughput, the row group concept is really becoming the fragment concept here, and that means in the file level, we don't really need the row group. That is, I think, what Chan also talked about, the so-called row groups considered harmful, because first of all, we really don't need that from the design perspective. That simplifies things quite a lot. And at the same time, that is really harmful for storing multimodal data like images, because like you either have super big row groups in order to accommodate for your images, or you have super small row groups, and those are really inefficient for read as well. So the row group concept can just really be removed at this point of time, so that we are just dropping data pages after data pages, and have a very wide column layout for our data. And this is, I think, talked more in our previous VRDB paper for people who are interested. I'm not going into too much details on this. And at the same time, once we have this kind of idea, we can also do some optimizations just for multimodal data. Because if we look into the graph here, I was saying dropping pages, but for multimodal data, especially if you think about images or video clips that you are feeding into LLMs, for example, those things don't really need to be stored in pages, right? They can be stored out of line. I can just store those as binary offsets, and then the pages just recorded offset. That will be much more efficient comparing to trying to put the multiple data into the page constraint, and the page, like similar to row group, have to be either too big or too small. So that is what we did for the blob encoding, which is to have this specialized encoding so that in the file level, you can just store the images and videos out of line, and then you can store the positions of that. And then when you are trying to read it, we give like a special blob API so that you can try to consume that. So if you think about in the GPU training process, for example, you want to train an embedding and append that as a new feature, then you are essentially pulling all the images and videos into your GPU directly without all the IOs, comparing to just store them individually. And then you can use the blob APIs to efficiently access those things. So this is how I think about that. So the lens format, file format, and table format combined together is really giving you I think the ultimate open source feature store that you can use for feature engineering. And I think open source here is really one of the key highlights, because that has been the direction that we have been pushing the open source, which is the almost next wave or next generation of the open lakehouse architecture. That is the open multimodal lakehouse architecture. Because if you see this graph, this is exactly the same shape like 10 years ago. Like 10 years ago, the left is the data warehouse, the right is the data lake, right? And the left is like, I have to load the data into different systems because my data is in a closed data warehouse system like Oracle, or even Snowflake is like that, right? And then I move into a data lake-driven architecture, or lakehouse-driven architecture that is like Hive tables, Delta Lake tables, Iceberg tables, Iceberg lake houses, those kind of things. But then for the machine learning side, you didn't really solve the issue for full text search, for vector search, or for other very lightweight SQL use cases. And then the multimodal lakehouse is really bringing the AI perspective also into the whole lakehouse architecture, so that you can really achieve everything, almost every I would say offline use cases through the single multimodal lakehouse architecture. And that's kind of, I think, why we are really gaining adoptions across the whole industry from the big companies into the frontier labs, also to different research institutes in different companies. What is very interesting is that when I was in Amazon, like I was in the wave of the so-called open table format battle war between Iceberg versus Delta versus Hoodie, and then we see the backing companies all showing up the labels here. Somehow they're also all using Lance now, so which is kind of exciting, right? So, and going back to the problem we were just talking about, like the expectation is not really meeting the reality. The storage is just one part, and the compute is really the second part, is that how do we compute all these new features at scale? Like once you have the storage figured out, and you store really a large amount of data in the storage, how do you scale up your compute in order to efficiently be able to process against the storage, right? And now here's an example, like a more complicated version than the image one I just showed you. This is also a simplified version from one of our customers, the Runway ML, which is a frontier video company, video model company. So you can see that they have videos, and they kind of get images of the videos, and then they also have audios derived from the video. So they have like three tables. And then they do this kind of data evolution thing to produce new features for all their tables. And it is still not a, I think one thing is that these transformations could be decoupled, right? You don't have to have dependencies between them, although you actually have dependency. For example, one feature might depend on the other one. However, you can always run a data evolution as, for example, backfill everything that is now, for example, that doesn't have a value yet, so that I can always catch up without knowing that my upstream has fulfilled or not. Although you might want to do that more efficiently anyway. But what really needs to happen is how I can efficiently do all these diamond shapes like at large scale. And that is really, we probably need a distributed engine to do that. We cannot really do that in a single machine. Although there are very efficient single, like embedded frameworks like DuckDB, Data Fusion, or even LanceDB open source itself is an embedded engine. But in this kind of thing, you probably need a distributed engine to distribute the work. One of the options that commonly talked about is probably Spark. That's I would say the most popular in the Western world. Like if you talk to the Asian people, they might say like Flink or those kind of things. But in US, in Europe, Spark is probably at this moment the most mature ecosystem. You can use PySpark, and especially for enterprise, the JVM people really love that. And then you have a standard distributed engine architecture that you have a driver that tries to plan out the tasks, and then you submit the task into the worker nodes. And if you're interested in that, I had a talk previously. You can search for that on the YouTube to read more about that. But here we are at PyData, and many of the people, I think for PySpark would say that I don't want to see Java stack trace in my Python execution, and Ray is really the kind of the replacement for that. And from architectural perspective, it's really similar to Spark. You also have the driver and the worker. And it's actually coming from the same Berkeley lab. I remember when I was in Berkeley, I was actually in Berkeley for my undergrad. And when I joined, Spark was like just born, and it was super popular. And then when I tried to apply for a research job in the AMP lab, in the RISE lab later. And then that time they were doing like Ray, and I was rejected. I think Ray is a bit lower level, so that there are like compute engines such as DAP built on top of Ray. From the user experience perspective, it's a bit more friendly for Python users. It's so-called Python native. Like if you talk about Python native ecosystem, Ray is usually a part of that. And also, I think one advantage comparing to Spark, although maybe Spark people will say otherwise, but I think it is more optimized for dynamic task graphs. That means for interactive workloads, which feature engineering is a part of, like you have to do some feature engineering and see how it works, and then you do some more, right? You have this interactive workflow. Ray is a bit better at that, I think, at this point. And then we're at the PyData conference, so we probably want to talk about Ray. So, and there are, of course, other options, I think, but not as wide ecosystem. And also, I just said that there are engines also built on top of Ray, like Daft. Also, Data Fusion Ray is a part of that. But I think for the feature engineering case, we really just need a mapper here. So it is probably not worth the complexity, in my perspective, to go with those options. And for integration with Lens, we do have a dedicated integration called LensRay. It's as easy as do pip install for that. And then you can kind of do basic read and write. You might notice there's like an official, I won't say official, like an old Lens connector directly in Ray data, but that is kind of out of date. So this is kind of like the new one we just wrote with latest features in a separate LensRay project, because we want to achieve, of course, more than just read and write. So here is, if you want to do read and write, you can just do something like that. You can do like import read lens, import write lens, and you can write data into that and specify a path for your lens data, and then you can write to it, and read that back. Something worth calling out is how that is actually executed in the background. For example, I have let's say a local environment, and I'm submitting my execution into a remote Ray cluster, and I do like read lens, this location, and I have these columns and these filters. And the commonly called predicate pushdown and column projection optimizations all work. Like we distribute at the fragment level, so that in the Ray Walker, you see every single fragment, and you process those individually. And for every single fragment, there's what we call the lens scanner. That is a part of the Lens core SDK. It is available in Python, also in Java, in Rust, in different languages. And in the end, it will take in all these columns and the filters, and it will consult all the indexes if it's available to do all the predicate pushdown and column projection. And column projection, of course, because Lens is a columnar file format. And then in the end, it gives you the error batches that is returned back to the user as results. And those are kind of important because when you are doing feature engineering, you probably want to read the data in the end to see how it looks like. And then the next thing for feature engineering, the most important part is really add columns. This is essentially the data evolution part of the whole thing. Now here I'm giving a very simple example. That is, you have a column called score, and you want to just double that. So you define a function, and then you will run add column against the function, and you can specify things like concurrency for running for how much concurrency you want to use in Ray. And going back to the example I was showing, then it is actually every single diamond box here becomes what I was just showing, the UDF that you define as a pi arrow transformation from one record batch into another record batch. And the add columns essentially just does the magic for invoking the array and does the transformation back to back. And how that and the execution is actually pretty much the same as what was shown here in the read pass. That is just that you are, instead of distributing the read, you are distributing the write, and the write is still distributed at the fragment level. And then the next part is going enterprise, because what I have been showing is that how you operate with the Lens data set kind of directly against storage. And when you go to enterprise, you probably want things like governance or those kind of things. That is what the namespace feature gives you. That is allow you to bridge between the different catalogs, meta stores, meta lakes, like unit catalog, have meta store, all those kind of things into Ray. And here's an example of using Ray with, for example, Unity namespace. That's how we call that. So that you initialize the namespace as Unity with whatever parameter you want to put, such as where is the endpoint, Unity endpoint, and assuming that you have a table in database one called myTable that is Lens, then you can write to that, and you can add columns just like what we were talking about, doubling your score, and then you can have the updated data stored in unit catalog with centralized governance, all those kind of good things. And you can still do the read. For example, here's an example that does a filter for double score is greater than 100, and then do a count. So all those kind of thing works. Also, when you are having the Lens data in the enterprise end. And there are some other features. That's actually a big reason why we put LensRay as a separate project instead of keeping that as a part of the array data core connectors is because we want to do more than just read and write. Data evolution is one of that. And there are also features added like distributed index building for B-tree and full text index. There's also, most recently, Netflix added the compaction, distributed compaction for lens tables, also in array. So you can almost do the whole data from attendance to feature engineering to read and write, everything using lens array at this point. And there are some upcoming features such as doing vector index distributed building using array. And there are also some thoughts about, if you know small pond, that is kind of an extension array that was published by DeepSeek. And there are some thoughts in the community about doing something like that for lens array. So keep up to date on that. And there are, of course, some performance improvements we can do. One of the improvements that is kind of obvious is in the distribution phase. Today we are just distributing fragments, but fragments is like every time you insert, you insert data, then you add new fragments. That means the fragments can be big or small before you really compact that into a uniform size. And that means some worker might run a long time, some workers might run a short time, and those might get imbalanced. So one thing we are doing right now is to make that more balanced so that we do slices of fragments and then do the transformation against that, and then commit it back. So there's some work going on with that as well. Yeah, and in the end, it is many thanks to all the community contributors. This is actually, the whole Lens3 project is a community-driven project. And these are all the companies that have worked on that to make it happen. So really a great shout out here for everyone who has worked on that and keep working on that. And a big reason that is a community project is because for LensDB Enterprise, we have built something like prior to Lens3 and dedicated for feature engineering that we call Geneva. It's also using Lens Array as a backend for storage and compute, but it offers kind of more features. One important thing, for example, I talked about previously is that once you have dependencies, how you handle the dependencies between columns, and those kind of things. And also we add fault tolerance to our own array distribution. And we added adaptive batching that is kind of similar to what I was talking about chunking the fragment, but more at the lower level. And for example, for materials view, you can get a small section of the view of the table and then do experiments just against that in an isolated environment, and then get the data back and then apply that to the whole table. So all those kind of things, and also of course caching to make things run faster. So we also have that as an alternative, but also build on array. So most of the concepts that I talked about applies there. And yeah, in the end, thanks everyone. I have the links for GitHub for people who are interested. Also some docs about the array integration, what is Geneva, and all sorts of blogs if you are interested. And again, we are hiring and we'll have a Discord if you want to join. Thanks everyone.
We have 5 minutes for questions. Does anybody have any questions?
Yeah, great talk, Jack. So for the data evolution feature in Lance, regardless of the content of the column, do you always just create another file? Meaning, even if it's just an integer, right, and you update the Lance table, are you basically just going to, as you keep on adding these columns, create new files? And if so, does that create like a small file problem?
Oh, that's a great question. Yeah, yes, if you don't do compaction, then for sure. And also, notice the function name is called add columns. That means you can actually add multiple columns. And what happens is that it's added as struct. So that kind of mitigates the problem, but it doesn't solve it. And in the compaction side, yes, you can compact all the small added columns into a single file so that it is more performant for read. There's an ongoing effort to say that let's define a concept called the old school concept called column family, so that we can always know that how you can organize what's your ideal way to organize those features into different families of columns so that those always stay in the same file because those are maybe usually often read together. So that is the ongoing effort we are doing.
Thank you.
Actually, I work for Spark community, so I'm one. Just a question. For example, if the Spark add a new data type blob, then what is the advantage of Lens compared with it? Because we can just like store the location pointers of this like video image files directly. So then we can just use a packet to store all these things and basically the logical data type of blob in like Spark or Iceberg or Delta. What do you think?
Yeah, that's a great question. I think in this case, there's always the what I would say the pointer approach, right? You have storing a pointer and that points to some location in the object storage, and then you go from there. I would actually recommend. There was just a Ray Summit a few days ago, and there was a talk between us and Netflix that talks a lot about why we think storing data inline is much more performant and much more manageable in ML training and those kind of things. One of the use case I would say is, for example, when you are doing GPU heavy work, then it gives you much less I/O between object storage and the GPU, so that you can let the GPU do more work rather than just waiting for data. So all those kind of things, and at the same time, I think the blob encoding, for example, what I was talking about, I think that is kind of recommended for the data that you want to feed into LLM, which means roughly 1 megabyte or less for images, or like 5 megabytes or less for videos. The LLM cannot take larger than that anyway. But when you talk about even larger size data, that in those cases, then storing that inline might not be the best option, and storing a pointer might be the best option. But even in that case, I think what we are doing is that there can be a middle step, which is you store multiple images in a single file and you point the pointer to different positions in that. Or if you have really big files, such as I want to store the raw video as a column, then that's fine. You can store that as a pointer. I think in that case, storing a single point is the way that makes the most sense. Maybe storing a bit more metadata alongside that. So that is a ongoing project called Blob V2 that we are doing at this point. But those are kind of all within the Lens format itself, so that you give a overall management of all these blob data types instead of they really being segregated between you have a format controlling just the pointers versus you have another bucket of things that you have to care about it. Did I expire that? Are there duplicates? All those kind of things. So all these kind of things are kind of managed together, expire together, or work at the same time. That's how I see it.
Okay.
Well, does Iceberg do that? Can Delta do that? Of course. I think it is a storage layer problem. And for Spark, it's more like, can you have the compute to be able to run that? I think we actually did add blob support in Spark Lens connector. And even there was just a feature added to even do this exact thing, the data evolution, also in Spark. So that is actually available today. So things are, I would expect things to even up, but in the end, it's more about giving the best experience to the people who are using it. Yeah.
Okay, just follow-up question. So because you inline this video image data to the files, right? So how to handle the duplicate? Like for example, multiple actually entries are actually points to the same file. If we inline the data, then does that just cause the data duplication?
Yes.
Okay, then it might be the storage size will be much bigger, right? For example.
That I'm curious. What is the use case you will store multiple rows pointing to the same image?
For example, people just like let's use an example like ChatGPT, right? So people maybe upload the same files, by different user in different sessions. So then we don't need to store this like uploaded files, same files into different rows. We basically can everybody can just point to the same file if they are same.
I think I agree with that. In that case, storing point is more efficient. That's also why we are supporting that, just in I guess a more user-friendly way. Yeah.
Okay, so LensDB can handle this case. I mean, to avoid the deprecation.
That is work in progress. I guess in end of December. Yeah.
Okay.
That'll be out. Yeah.
Okay. Cool.
We'll take one last question before we take lunch break.
Hi, thank you. I wanted to ask a little more about the integration between Lens and Ray. I know that one of your slides had something about indexing inside the database with Ray. And I was wondering if you guys are using the object store from Ray at all, or how are you interacting with the distributed object store inside Ray to handle some of the data requests that you have with Lens?
I'm actually not familiar with that. Does Ray have like a native object store?
Yeah.
Or is that just like
it's basically
kind of Ray's internal storage?
It's Ray's internal storage. It's a key value store that Ray has, and it's distributed. And it's actually shared.
Okay, I see what you mean.
It's a shared memory, so it's one of the efficiencies that you get by running on Ray.
I see what you mean now. Okay, for that, currently all the index building are directly against like the cloud object storage. Because all the indexes in Lens are a part of the table format, so all the indexes are also a storage format defined. You can store that in object storage. Mm-hmm. And for example, for B tree, what we do is you build the sorted B tree for different, well, not sorted B tree, the sorted list for like sections of the data, and then you do an n-way merge, all those kind of things. Actually, there is an ongoing discussion about actually can we leverage the Ray shuffle, which will use the Ray internal object storage, I think, to improve that performance. So I think as we start to do more complicated index building, those will for sure be leveraged.
I see.
Yeah.
Okay, so in theory, all the data requests are going straight to Lens and it's back in storage as opposed to
like the initial data retrieval and the final output will always be in cloud object storage.
Sure. Yeah.